Uncertainty in artificial intelligence refers to the lack of complete information or confidence in the outcomes produced by AI systems. It often arises due to incomplete data, inherent unpredictability in real-world scenarios, or limitations in the algorithms used. Techniques like probabilistic modeling, Bayesian inference, and uncertainty quantification are employed to manage and mitigate uncertainties in AI systems. Basic probability notation includes 1. Sample space is the set of all possible outcomes of a random experiment. 2. Event is a subset of the sample space, representing one or more outcomes of interest. 3. Probability is the likelihood of an event occurring, denoted as P, E, where E is the event. 4. Complement is the complement of an event E, representing all outcomes not in E. 5. Union EF the event that either E or F, or both, occurs. 6. Intersection EF the event that both E and F occur simultaneously. 7. Conditional probability P, E vertical bar F, the probability of event E occurring given that event F has occurred. 8. Independent events E and F are independent if the occurrence of one does not affect the probability of the other. 9. Bayes theorem, a formula to calculate conditional probabilities based on prior probabilities and new evidence. Inference using full joint notation involves analyzing the joint probability distribution of all variables in a probabilistic model to make predictions or answer queries about the system. Given a set of random variables \x_1, x_2, x_n their full joint probability distribution \p, x_1, x_2, x_n captures the probabilities of all possible combinations of values for these variables. Inference using full joint notation typically involves 1. Marginalization, summing or integrating out variables from the joint distribution to obtain the distribution over a subset of variables of interest. For example, to compute \p, x_1, from \p, x_1, x_2, x_n you sum integrate over all other variables. 2. Conditional probability, computing conditional probabilities using Bayes' rule or directly from the joint distribution. For example, \p, x_1 vertical bar x_2 can be calculated as \frac p, x_1, x_2, p, x_2 \. 3. Inference, making predictions or answering queries by combining information from the joint distribution with observed evidence or prior knowledge. Independence in probability theory refers to the lack of influence or correlation between random variables. Two random variables \x and \y are considered independent if the occurrence of one does not affect the probability distribution of the other. Formally, two random variables \x and \y are independent if and only if \p x_y is equal to p x times p y \. This means that the joint probability of \x and \y occurring is equal to the product of their individual probabilities. In other words, knowing the outcome of one variable provides no information about the outcome of the other. Bayes' rule, also known as Bayes' theorem, is a fundamental concept in probability theory that describes how to update beliefs or probabilities in light of new evidence. It is named after the Reverend Thomas Bayes, an 18th-century statistician and theologian. The formula for Bayes' rule is \p a vertical bar b is equal to \frac p b vertical bar a \times p a P, B, backslash. Where backslash P, a vertical bar B, backslash, is the probability of event A occurring given that event B has occurred, the posterior probability. Backslash P, B vertical bar A, backslash, is the probability of event B occurring given that event A has occurred, the likelihood. Backslash P, A, backslash, and backslash P, B, backslash, are the probabilities of events A and B occurring independently of each other, the prior probabilities. Bayes' rule is particularly useful in situations where we have prior knowledge about the probabilities of events, and we want to update these probabilities based on new evidence. It is widely used in various fields, including 1. Statistical inference. Bayes' rule is used to estimate unknown parameters in statistical models, especially in Bayesian statistics, where prior beliefs about the parameters are incorporated into the analysis. 2. Machine learning. In machine learning, Bayes' rule is employed in Bayesian inference algorithms, such as Bayesian networks and probabilistic graphical models, for tasks like classification, regression, and clustering. 3. Medical diagnosis. Bayes' rule is used in medical diagnosis to update the probability of a disease given the results of diagnostic tests and prior knowledge about the patient's health. 4. Natural language processing. In NLP, Bayes' rule is used in text classification tasks, such as spam detection and sentiment analysis, to update the probability of a document belonging to a particular category given its features.